Hi, everyone. Thank you for tuning in if you're watching online. So I'm James. I'm from the Canadian Institute for Theoretical Astrophysics at Toronto, and I'm going to briefly go through some of the work I've been doing looking at the DM variations of the NANOGrav Pulsars using CHIME data. So quick overview for people who aren't familiar. CHIME is a new telescope located in British Columbia in Canada. It's been up and running in continuous operation for about the last year and a half or so, coming up to 2 years. So while CHIME is very famous at the moment for the work it's doing with fast radio bursts, it's also a very useful tool for timing pulsars. Some of the reasons for that are the large fractional bandwidth that we have. We observe in the 400 to 800 megahertz range with relatively high frequency resolution recorded natively, which gives us very high precision to interstellar medium effects and in particular DM variations. So in addition to this, we have very high observing cadence. Typically every 1 to 2 days, we observe every pulsar in the sky, which is ideal for looking at some of these small scale rapid variations that we are sensitive to with a telescope like CHIME. So we can't see all of the NANOGrav pulsars. We have a declination range limit of above approximately minus 15 degrees. And there are some pulsars that we've ceased to observe just because they're very faint at CHIME frequencies. So in all, I have a 37 pulsar data set at the moment. So the first thing that I do is I run my TOA generation pipeline that takes a frequency resolved observation and fits a two-dimensional template to it. So a 2D template looks something like this in the case of 1012 plus 5307. So instead of fully scrunching in frequency, we instead scrunch to 64 frequency channels across our 400 megahertz of bandwidth. And for each of these channels, we generate a TOA from a single observation. So before I forget, this is something that I worked on a lot with Jacob Tremblay, an undergrad student at WVU over the summer. So he's put a lot of very hard work into this, and he's produced some really nice results with it. So we do a lot of the basic stuff that would go into a pipeline, which is installing the new or installing a consistent ephemeris into all of our observations, doing some cleaning based on this tool created by Lars Kunkel in the University of Bielefeld. And yeah, we go through and generate a TOA for each one of these channels. So after that, on an observation by observation basis, we simply go through the TOAs, run a relatively simple maximum absolute deviation algorithm to remove any outliers due to RFI or low signal in the channel. And then we just fit for DM. So the example I'm showing here uses J0218 plus 4232, where before the fit, we can see that we have this very typical looking frequency to the -2 trend in the residuals as a function of frequency. So we just simply fit for that, and we get our DM that way. So in the case of this diagram that I'm showing here, the difference between the first plot that's very clearly got the wrong DM and the post-fit plot is only 8 times 10 to the -4 DM units. So in the case of this pulsar, we're very, very sensitive to small DM variations in this pulsar. So I can go through and just really quickly show you the time series that we have for our pulsars. So the green data points are the DMs obtained from the single observations. This purple shading is a running mean that I'm using to help us better pick out some of the trends in the data. And for all of the pulsars, I've plotted this orange dashed line, which is the closest approach to the sun, the closest angular approach to the sun. Up here, this beta number is the height above the ecliptic plane. So pulsars with a very small beta go quite close to the sun, and we might expect them to be affected by the solar wind when they approach the sun. So we can see that a little in like J0030. There's maybe something of a bump there, but the precision is relatively low. We can definitely see it in some of the other pulsars, but while we're on this slide, I'll just highlight 0218 from that I was using in the example before. So this pulsar has extremely large and rapid DM variations that we can beautifully resolve with CHIME. So this has been used as quite a nice test case while developing the pipeline. Most of the others are relatively flat, with maybe some kind of wobbling going on, which is more or less to be expected given that we only have about 1.5 years of data at this point. And from what we've seen in other studies of PTA pulsar DM variations, the ones that display trends typically take place over much longer timescales than the current length of our data set. 0621 is an exception to that. This is a pulsar that's known to have a very fast and, well, initially we thought linear change in DM over the last few years, but it appears to have leveled out in the last year or so. So flipping through some more, we can see 1022 shows a really, really clear solar wind signal, this kind of annual sinusoid that has the maximum rate at the solar approach. This pulsar is by far one of the ones that approaches the sun the most closely, so it's not entirely unexpected. Another pulsar that I'm going to look at in detail before the end of the talk is 1937 plus 21, which again is very well known to have large and rapid variations in its DM. So we've decided to use this as something of a test case. But just to quickly move on to this kind of summary slide, we can see that the mean cadence is very high for all of these pulsars. It's more or less under 2 for everything that we have. The median DM error is also quite large. In most cases, it's at the 10 to the -3 DM units level, but in the case of a few of them, it's at the 10 to the -4 level, or even lower in the case of 1937. So looking more carefully at 1937, we are using this to develop some of the techniques that we're going to eventually apply to the entire data set for this work. So this is things like looking at the structure function. Now we only have a short data set, so we maybe can't really see that much of interest at the moment, but we can certainly resolve the basic shape of the structure function. The other thing that we're very interested in looking at is evidence for plasma lensing. So this is similar to what Fangxi Lin has done with the 1713 DM events. He's outlined this process in a lot more detail in a paper that is, I think, submitted. It's more or less finished anyway, but he's applied it to observations of the 2051 Black Widow pulsar, this wonder eclipse that had all sorts of interesting propagation effects going on. So the upshot of what we're looking for is we need very, very rapid changes in DM. So ones where we have a very strongly measurable DM second derivative, because things like that are expected to arise from plasma lenses actually bending the light rather than just simply changing the observed dispersion measure, just acting exactly like a glass lens, but for radio waves. So if we take this this one particular part of the data set where there's this very, very rapid drop off in DM and try to model it, we can find a few interesting things. So up here, I just have in blue the data with the very basic error bars kind of plot over this. And I have a very basic model for a DM, for a plasma lens, like a wedge-shaped plasma lens, that I've more or less been able to fit to the event. This will be familiar to people who have followed the DM event work in 1713. But the interesting thing is that if we model this event as such, we start to get predictions of a bending angle of 174 milliarc seconds, which corresponds to a time delay of 128 milliseconds, which is absolutely enormous. In fact, it's so enormous it doesn't make any sense. The reason for this, though, is probably because our first pass at modeling this assumes that the lens is a thin screen halfway between the Earth and the pulsar. So the canonical kind of assumptions that go into this. And it clearly doesn't work. I mean, we can see a huge drop-off that is in the data set that looks consistent with plasma lensing, but the numbers that come out are enormous. So something that we're starting to explore is that, assuming this is due to a plasma lens, it can't be anywhere near halfway towards the pulsar. It has to be extremely close to the pulsar, like basically in the same vicinity as it. So this is kind of early at the moment, but we intend to go through all of 1937's data sets and try modeling some of these DM events as plasma lensing events. This will eventually be expanded to other promising pulsars in the data set. So I'm going to end it there. Some of the other things that we want to do are compare the DMs that we've measured to those from NANOGrav, maybe plotting them together and things like that. So if you're listening to this and you would be interested in into looking into that with me, please just get in touch. We can set something up and see what we can find. We're going to go through the rest of the data set, looking at the turbulence statistics with the structure functions, hopefully being able to probe very short timescales. We're going to explore these plasma lens models, especially with 1937. And we're going to look into the solar wind influence on some of these pulsars. So this is the time where I'd ask for questions if anyone is still listening, but if you do have questions, just send me a message on Slack or an email, and thank you very much.